Autonomous mobile navigation requires a robot to perceive its surroundings, reason about hazards, and chart a minimum cost route to a goal, all without human intervention. A primary challenge in robotics is translating the infinite, continuous nature of physical space into something a processor can navigate. In this specific framework, we address this by partitioning the environment into a structured, finite model. To solve this, we translate the physical geometry of the real world into a searchable topological graph. This conversion relies on the point mass paradigm. It is an algorithmic simplification where we treat a complex, multidimensional robot as a single dimensionless coordinate. Operating on a single point simplifies the math. Instead of tracking the footprint of the entire vehicle, the algorithm only has to track one unit as it steps through space. But this simplification creates a physical risk. If a dimensionless point charts an optimal trajectory that grazes an obstacle, the actual physical chassis of the robot will collide with the environment. Today, we are deconstructing the front-end pipeline of autonomous navigation, specifically the environment modeling, topology mapping, and heuristic selection that makes safe, optimal path planning possible. Using a grid-based matrix as the search space creates a clear, deterministic landscape. This architectural choice provides a reliable way to guarantee that a route is both computationally efficient and strictly collision-free. The foundational environment representation is the occupancy grid. This image displays a raw occupancy grid. The physical workspace is divided into discrete cells, defined by a size parameter called delta. The grid operates on binary logic. 0 denotes free space, while 1 marks an occupied obstacle, represented here by solid blue blocks. As we established earlier, an algorithm charting a route for a dimensionless point through these free cells will cut corners too closely, causing a physical robot to strike these boundaries. This panel shows the geometric solution, obstacle inflation. Here, the exact same environment is plotted with expanded obstacle boundaries. This is achieved through morphological dilation. The boundary of every occupied cell is artificially expanded outward in all directions. The expansion parameter is exact. The inflation radius is set precisely equal to the physical radius of the robot itself. This provides a strict mathematical guarantee. If the calculated path for our point mass stays within the free space of this inflated grid, the physical robot's chassis will maintain physical clearance. Obstacle inflation solves the physical safety problem within the map's geometry. This frees the downstream search algorithm to operate purely as an unconstrained mathematical optimizer. Once the safety boundaries are established, the raw grid must be converted into a graph of nodes and edges so an algorithm can traverse it. The simplest approach is a four-connected topology, where movement is strictly limited to orthogonal directions, up, down, left, and right. But four-connectivity forces jagged paths. It restricts movement in a way that fails to reflect how a robot naturally navigates physical space. The superior solution for mobile robotics is an 8-connected topology, which adds diagonal connections between the center node and the four corners. To maintain geometric accuracy, we must assign precise mathematical edge costs to these new topological paths. The cost of a direct orthogonal move is exactly delta, and the cost of a diagonal move is delta multiplied by the square root of 2. Strictly enforcing these specific edge costs ensures that the algorithm's virtual steps perfectly mirror physical Euclidean distance, preventing geometric distortion during the path calculation. With the graph constructed, we deploy the A-star search algorithm. Its objective is to find the minimum cost sequence of free cells from the start node to the goal. A-star relies on a core cost evaluation equation. F of n equals g of n plus h of n. The variable g of n represents the exact accumulated cost of the path traversed so far. The variable h of n is the heuristic function, the algorithm's mathematical prediction of the remaining distance to the goal. There is a strict rule for any A-star heuristic. It must be admissible. It must mathematically guarantee that it will never overestimate the true remaining cost. Standard heuristics have limitations here. Using a straight-line Euclidean or a Chebyshev heuristic introduces search inefficiencies when operating on an 8-connected grid. Instead, this framework utilizes the octile heuristic. The octile heuristic calculates the absolute tightest admissible lower bound by perfectly accounting for the specific mix of diagonal and orthogonal moves required on an 8-way grid. This image displays the nodes expanded by A star. Notice how the octile heuristic aggressively biases the search directly toward the goal, forming a narrow, efficient band of colored dots rather than exploring blindly in all directions. When the heuristic aligns with the underlying topology, the algorithm explores fewer unnecessary nodes. This reduces the search time, allowing the navigator to process complex routes with significantly fewer computational cycles. Once the algorithm reaches the goal node, it executes its final step, tracing parent pointers backward from the destination to the start to reconstruct the definitive optimal route. This graphic shows that completed A-star path in orange, navigating successfully through the obstacle field. The path utilizes diagonal moves and safely hugs the perimeters of the obstacle blocks without colliding, verifying the success of both the topology and the inflation protocols. The integration of the discrete grid, obstacle inflation, 8-way topology, and the octile A-star algorithm successfully satisfies the core requirement of global path planning. However, this output contains a mechanical flaw. The generated path is merely a series of discrete, linear segments connected by sharp vertices. While geometrically safe for a dimensionless point, executing sharp 45 or 90-degree turns would require infinite acceleration from a physical robot. This sets up the necessity for the next phase of design, translating mathematical waypoints into continuous, mechanically feasible trajectories.